For our second experimental design question, we have a projectile here. Students are studying the two-dimensional motion of objects as they move through the air. Specifically, they're examining the behavior of a sphere that's launched horizontally from a location above the floor with an initial velocity v0 in the plus x direction as shown in the figure. The students assume that the positive directions are along the sphere's initial velocity for horizontal motion and downward for vertical motion. That's shown in the diagram as well. The horizontal displacement of the object from its starting point is x, and the vertical displacement of the object from its starting point is y. One of the students derives an equation for y in terms of x and other quantities. After examining the equation, the student claims that y is proportional to x squared. So, A, derive an equation for the vertical coordinate y of the sphere as a function of x, v0, and physical constants as appropriate. Now, the physical constant in this case is little g, acceleration due to gravity. So what do we have here? We never did this very much specifically in our projectile unit because we were busy actually calculating numbers, but we know that the distance it's going to travel is equal to the horizontal distance times time because the horizontal velocity is all in the x direction, as you can see in the picture. So there's our set for where it is x-wise. Where is it y-wise? Now remember, positive y is down, so we don't have to worry about all the negative stuff. We're going to use this formula, delta y is equal to v initial t plus 1/2 at squared, which you should really have in your back pocket at this point. The initial y velocity is 0 here. Acceleration due to gravity is 9.8 meters per second squared, or little g. So this is going to become y equals 1/2 gt squared. Now, we need to solve for y in terms of x. As you know, our bridge is t, right? So from here, we're going to say, well, t is equal to x over v0. We're going to plug that in here, and we're going to get y equals 1/2 g, and then x squared v0 squared. Okay, and you're fine with that as your answer. You could simplify it to something like g over 2, x squared over v0 squared. Don't waste a lot of your time simplifying. What I've circled is good. So 1 point for the appropriate kinematic equations for the x movement and the y movement, and then 1 point for combining using t. That should be pretty quick to the front of your mind because t has always been our bridge between x and y movement. So there's 2 points for part A. So in part B, we're going to actually take some data and measure some x's and measure some y's. So let me look at the diagram while I'm reading this and realize that it's not quite so bad. And if we were in class, we would have done this. The students have access to the experimental apparatus shown above in the figure. Besides the sphere, the apparatus consists of a launcher that launches the sphere horizontally. That's where it says launcher, vertically movable. So I can vary the height of that, okay? This launcher will always launch with the same unknown speed, v0. So we can't change that, right? The stand that can be used to adjust the height of the launcher. So you can probably see, oh, we're going to do this a lot of times at a few different heights because I can't vary the initial speed. The students also have several sheets of plain paper, several sheets of carbon paper, a meter stick, and a stopwatch. Whenever the sphere bounces off the carbon paper produces a visible mark on the sheet of plain paper that's underneath the carbon paper. So you put the carbon paper on top of the regular paper, you get the ball to land on the carbon paper, and then it makes a mark. So that's how you can measure the horizontal distance that the ball travels. So B says to design an experimental procedure that you could use to test the claim that y is proportional to x squared. So in the table below, list the quantities and symbols that would be measured in your experiment and how you're going to use them. So you don't need to fill in every row. If you need additional rows, add them. You don't need much for this. All you need to measure, if you're going to use this formula here, you need to measure your y's and you need to measure your x's. So we're going to measure the y by simply measuring the vertical distance between the sphere and the ground at launch with the meter stick. We're going to measure the x distance with the plain paper and the carbon paper, and again, a meter stick to determine that. Now you can find the time by using delta y, right? So you don't need the stopwatch. So I would not include the stopwatch in my procedure here. So what you'd want to do is you want to launch it several times and vary the y. That's all you can vary here. You cannot vary V naught because it says it launches always at the same time, and you can't vary G because you're doing this on Earth. So how am I going to do this? I'm going to do it at several different heights, and I'm going to do it a few times at each height. So if you can vary two things, I feel like 3 trials is fine. So 3 trials at a low height, 3 trials at a medium height, and 3 trials at a higher height. However you want to do that. This is where you can use different symbols if you want, and they'll follow along with you, but make sure you use something that makes sense to you. So for part B, 1 point for listing the relevant equipment and quantities. So you wouldn't say, oh, I'm going to use a timer to measure the distance, right? That's what they mean by relevant and appropriate. So I use meter sticks to measure distance. I use timers to measure time, even though I'm probably not going to use that in this experiment. 1 point for explaining how you'd verify this claim. 1 point for measuring X, 1 point for measuring Y for at least 2 values. So they say at least 2 values of Y. And then 1 point for reducing uncertainty, either by using 3 different heights or twice at 2 different heights. So maybe they're okay with twice at 2 different heights. So that's part B, 5 points. So in part C, we're actually given some data, some X data and some Y data. And we want to use the teacher's data to determine whether the claim is true that Y is proportional to X squared, right? That means Y is equal to some constant times X squared. So what are we going to graph? Well, the formula that we've sort of figured out here, 1/2 G over V naught X squared, means that this would be our constant of proportionality, right? So what are we going to want to graph here to see if this is a linear relationship? So I think the best answer here is to graph Y in meters on the y-axis and graph X squared, which would be in meters squared, on the x-axis. Then if it comes out as a straight line, then we know that Y is proportional to X squared. So here's how the points break down for part C. For II, which says to actually graph it, okay, 1 point for a scale that uses at least half of the grid correctly labeling axes and units. So if you're graphing Y versus X squared, make sure you label that and make sure you indicate the units. 1 point for plotting it correctly, because look, the data you're given Y and X. So you've got to actually graph X squared. So that's why if you wanted to add X squared in a column there, and we did this over the summer when we were linearizing data, if you want to have another column in your data table that's X squared, that's going to make it easier to plot. 1 point for correctly plotting. So don't confine yourself to the bottom left corner of that graph. Use as much of it as possible. You have all the data, so there's no excuse for running over or not using enough. You have the data. Use that to make your axes. The final point is for a reasonable justification that Y is proportional to X squared. So for me, if you graph Y versus X squared and get a roughly linear relationship, that's it. It's a straight line. You can do your R squared test, and if it's close to 1, you're good. Now, if you wanted to graph Y versus X, you could do that, but what would you get? You'd get a parabola, right? But you've got to justify that because not all parabolas are Y equals X squared, right? It could be Y equals 2X squared or Y equals 1/2 X squared. So if you're going to do this guy, you got to have that right constant, if you will. You must say that Y increases by 4 when X is doubled or something similar to that, okay? So just a parabola is not okay. You've got to do some more justifying. So that's why for me, Y is equal to X squared is the easiest. If you can linearize and get a straight line, you can't argue with that. A straight line's a straight line. So remember, we're not looking for V naught in this, although we could, but they're just asking to justify that it's a linear relationship. So that's it for part C. Now for part D, they're going to kind of backtrack on us, and they say what would the graphs of Vx and Vy versus t look like if we launched at a larger velocity? So the graphs below show the sphere's horizontal and vertical velocity components as functions of time. On the same graphs, sketch what Vx and Vy would look like for a different launcher that has a lower speed. Okay, so let's do X first. We know that, and I kind of like that they sort of start with they kind of start by telling you, okay, well, the X velocity is constant. If I have a new launcher with a lower velocity, the velocity is going to still be horizontal. The velocity is not. The horizontal velocity is still a horizontal line. It's just got a lower value, okay? Not lower than 0, and they don't really give you the option to do that. But here's my answer right here in the red. So 1 point for that. Now, what about the X? Excuse me. What about the Y velocity? Vy as a function of t, and here is 0. So here's what it was before. So we know that the Y velocity, remember, down was positive in this case. So the Y velocity gets more and more negative. But remember, the horizontal speed does not affect what's going on in the vertical direction. So the correct answer here is right along this line. Right, I didn't draw it perfectly, but that's what it looks like. So 1 point for that. So even if you went a little astray in parts B and C, again, never, never, never give up. Go to the end, because I guarantee you could have answered this question and salvaged those 2 points. So that's question number 2.